Picture an animal the size of a city bus, dropping straight down into water so dark and so heavy it would crush a car flat in seconds. No light, no air, just pressure that doubles every 33 feet. And it keeps going. We are talking about the sperm whale, the largest toothed predator that has ever lived on this planet. And the deeper it dives, the more dangerous it becomes. Tonight, we are going down with it. We will see what happens to a body at 6,000 feet, hear a sound louder than a jet engine, and find out what lives down there that is worth the risk. If you want more videos like this, hit subscribe. You will not regret it. Ready? We go down now. Pull up every scary predator you know. Great white shark, orca, saltwater crocodile. Now forget all of them. The sperm whale makes every other predator on Earth look small. We are talking about an animal that stretches 60 feet from nose to tail, that is longer than 2 school buses parked end to end. It weighs as much as 50 cars. And unlike the blue whale, which is bigger but eats tiny shrimp, the sperm whale hunts. With teeth, big, heavy, cone-shaped teeth, each one the size of a banana, lining a jaw so powerful it could snap a small boat in two. Scientists call it the largest toothed predator in Earth's history. Every creature on the list below it is significantly smaller. The next closest is the orca, which maxes out at around 30 feet. The sperm whale nearly doubles that. But here is where it gets strange. For an animal built like the ultimate killer, the sperm whale almost never uses its teeth to attack. It does not bite, rip, or chew. It opens that enormous jaw and creates suction so powerful it pulls prey straight down its throat hole. The teeth are mostly used on one type of animal, and we will get to that creature soon enough. A creature that fights back in ways you would not believe. The sperm whale's head alone takes up 1/3 of its entire body. That blocky rectangular skull is the most recognizable shape in the ocean. Nothing else looks like it. Inside that head sits a structure filled with a thick, waxy oil that scientists spent decades trying to figure out. They still argue about what it is actually for. 2 theories exist, and both of them are wild. We will cover those later, and one of them involves the whale physically changing its own weight to float or sink without effort. For now, focus on the scale of this animal. A sperm whale's brain is the largest brain of any creature ever known to exist on this planet. Bigger than a dinosaur's, bigger than any whale alive today. It weighs about 18 pounds, roughly 5 times heavier than a human brain. What the whale does with all that brain power is something researchers are still actively studying. They have found evidence of complex social behavior, long-term memory, and communication patterns that look almost like a language. Almost, the sperm whale lives in every ocean on Earth. It travels in tight family groups led by females. The males grow much larger and often roam alone across thousands of miles. They can live for over 70 years. And for most of those 70 years, they spend their time doing something that should be physically impossible. They drop into the deep ocean and stay there. 6,000 feet down. That is more than a mile below the surface. Down where the water is nearly freezing. Down where the pressure would flatten a human body in seconds. Down where there is no light, no warmth, and no air. And they do it over and over again, for their entire lives. Every dive pushes their body to a limit that evolution had to solve piece by piece. The solutions are stranger than anything an engineer would dream up. The first thing that had to change was the part of the body most vulnerable to pressure. The part that holds air. The lungs. The sperm whale does not dive 6,000 feet because it enjoys the dark. It dives because that is where the food is. Specifically, one animal. An animal so large, so powerful, and so well armoured that hunting it is one of the most violent things that happens on this planet, and almost no human has ever seen it. The giant squid. Most people picture a squid as something small and rubbery sitting on a dinner plate. The giant squid is something else entirely. It grows up to 40 feet long. Its body alone, without the tentacles, can be as long as a full-grown man is tall. Its eyes are the largest of any animal alive, roughly the size of a dinner plate each, designed to detect the faintest trace of light in near-total darkness. Its tentacles are covered in suckers, and each sucker is ringed with a serrated edge, like a tiny circular saw blade. When a giant squid grabs something, those rings dig in and hold. The scars they leave are circular, raised and permanent. Sperm whales arrive at the surface covered in those scars. Some whales carry wounds across their entire bodies, rings of scar tissue from tentacles that tried to fight back during battles happening in total blackness, more than a mile underwater, with no witnesses. Scientists have never filmed a live giant squid hunt. They have pieced together what happens from the scars, from stomach contents, and from the occasional piece of tentacle found in a whale's gut. What they know is this: the squid lives deep because pressure and cold preserve its soft body, and because light cannot reach it there, keeping it hidden. The sperm whale followed it down. Over millions of years, the whale's body changed to make that journey survivable, then to make it efficient, then to make the whale lethal in exactly that environment. The deep ocean did not break the sperm whale. It built one. The giant squid is not the only thing down there. Sperm whales also eat large fish, octopuses, and other squid species. But the giant squid is the trophy. It is the reason the whale needs to go so deep and stay so long. A single large squid provides an enormous meal. The energy trade-off is worth the risk of the dive. And the risk is real. Going that deep costs the whale something every single time. The pressure acts on its body in ways that accumulate over a lifetime. There is evidence that older sperm whales carry permanent damage in their bones from decades of diving. Not visible from the outside, but carved into the skeleton. The whale pays for every meal in the deep. But before we get to what the pressure actually does inside the body, we need to understand what pressure at that depth actually means, because 6,000 feet is a number that sounds big without feeling big. Here is how to feel it. At 33 feet underwater, the pressure on your body doubles compared to what you feel on land. At 66 feet, it triples. Every 33 feet you go down, another full atmosphere of weight presses in from every direction. At 6,000 feet, the pressure pushing against every square inch of your body is nearly 180 times what you feel sitting in this room right now. Your lungs would not compress. They would collapse. Your sinuses would fill with fluid in seconds. And that is just the beginning of what depth does to a body. Imagine standing at the bottom of a swimming pool. You feel it in your ears. That dull squeeze. That is pressure doing its job, pushing in from every side. Now imagine that feeling multiplied by 180. That is what waits at 6,000 feet below the surface. Pressure in the ocean works simply. The deeper you go, the more water sits above you. All that water has weight, and weight pushes down and in and up from every direction at once. At the surface, the air around you pushes against your skin at a standard level that your body is built to handle. Go down 33 feet and that pressure doubles. Go down another 33 feet and it doubles again. By 6,000 feet, the force pressing in on every single square inch of exposed surface is close to 2,600 pounds. 2,600 pounds per square inch. To picture that, imagine stacking a full-grown rhinoceros on top of a surface the size of a credit card. That is roughly the force pressing against every small patch of anything at that depth. For a human body, this is fatal within seconds. The first thing to go is the lungs. Lungs are full of air, and air compresses. The chest would cave inward as the lungs collapsed. The air spaces in the sinuses and middle ear would implode. Blood vessels near the surface of the skin would rupture. The whole process would be fast and total. Navy divers using the most advanced equipment in the world can reach around 2,000 feet with extreme preparation and support systems. Below that, even with a rigid suit, the engineering challenges become almost impossible to solve. The sperm whale does not use a suit. It goes twice as deep as any human diver has ever gone, using only biology. And this is where the whale's story stops being about a big animal and starts being about one of the most elegant biological designs on the planet. The human body fights pressure. It is built rigid where it needs to stay rigid and it tries to hold its shape. That is exactly the wrong strategy underwater. Anything rigid at depth becomes a liability. Pressure finds the air pockets, the hollow spaces, the gaps, and it crushes them. The sperm whale evolved to do the opposite. It gave up rigidity. It built a body that bends, compresses, and yields to pressure, rather than resisting it. And by surrendering to the force instead of fighting it, the whale survives it. The ribcage is the first place this shows up. In most large animals, ribs are solid, rigid arches of bone locked into place. In a sperm whale, the ribs connect to the spine and sternum through flexible cartilage. As the whale descends and pressure increases, the chest does not fight back. It gives way. The whole ribcage folds inward like a collapsing cage, and the lungs inside it compress along with it. A human ribcage breaking under pressure is a catastrophe. A sperm whale ribcage doing the same thing is the plan, and the plan gets stranger the deeper you look. Because when those lungs compress to almost nothing, the whale still needs oxygen to keep its muscles and brain running for the next hour. The air is gone, the lungs are flat, and the whale is still hunting. So where does the oxygen come from? At around 300 feet, something starts happening inside a diving sperm whale that would look terrifying from the outside if you could see it. The chest begins to cave in. The ribs, which in most large mammals are locked into a firm arch, start folding inward. The whole front of the whale's torso compresses. The space inside the chest gets smaller and smaller as the pressure outside gets bigger and bigger. This is not injury. This is design. Most animals that breathe air have stiff rib cages for a reason. The lungs need room to expand. Breathing requires space. A collapsing chest means something has gone wrong. For the sperm whale, it means everything is going exactly right. The key difference is in the joints where the ribs connect. In humans and most land animals, these connections are tight and bony, built to hold a fixed shape. In sperm whales, cartilage connects the ribs to the sternum and spine. Cartilage is softer than bone. It bends. It compresses. It allows the whole ribcage to fold under pressure without breaking or tearing the tissue around it. Scientists describe this as a compliant thorax, a chest built to yield. As the whale dives past 1,000 feet, the ribs fold further inward. By 2,000 feet, the lungs inside have compressed dramatically. By the time the whale reaches its maximum depth, the lungs have shrunk to less than 1% of their surface volume. Take a balloon inflated to full size. Now squeeze it until it is a tight, dense ball the size of a walnut. That is roughly what happens to the sperm whale's lungs on a deep dive. And here is the critical part. When the lungs compress that completely, the air inside them gets pushed out of the lung tissue and into the rigid parts of the breathing system, specifically the airway and trachea, which do not compress. The air moves from the soft, flexible lung walls into the firm tube connecting the lungs to the outside world. This is not accidental. This is a mechanism. When air sits in lung tissue, gas molecules can cross from the air into the bloodstream. That is how breathing works. Oxygen passes through the thin lung walls into the blood, but nitrogen passes through too, and nitrogen under high pressure dissolves into the blood in large amounts. If a diver goes deep with compressed air and comes up too fast, that dissolved nitrogen comes back out of the blood as bubbles. Tiny gas bubbles forming inside the bloodstream and joints. That is decompression sickness, called the bends, and it is agonizing and potentially fatal. The sperm whale avoids this by moving the air away from the lung walls before the pressure can force nitrogen across. The nitrogen stays trapped in the rigid trachea, where it cannot dissolve into the blood. The lungs go flat. The risk disappears. The whale essentially shuts down its own breathing system on purpose, mid-dive, to protect its blood. It is one of the most precise physiological tricks in the animal kingdom. But here is what makes it even more remarkable. The whale shuts down its lungs and keeps hunting for another hour, which means oxygen has to come from somewhere else entirely. The answer involves blood. A lot of blood. Blood that works differently than yours does. By the time a sperm whale reaches 2,000 feet, its lungs are essentially off. Flat, compressed, removed from the equation entirely. At the surface, a sperm whale takes a breath and holds it. That single breath has to last the entire dive, which can run close to 90 minutes. No refills. No air tanks. One breath, held for the length of a full movie. For a human, holding your breath for 90 minutes is impossible. The world record for a trained free diver, a person who has spent years conditioning their body specifically for this, is around 24 minutes. And that is lying still in calm water, not actively hunting a 40-foot squid in pitch darkness. The sperm whale hunts, chases, and captures prey during those 90 minutes. So the first question is obvious. Where does it store enough oxygen to do all of that? The answer starts with a number. Sperm whales carry roughly 3 times more blood per pound of body weight than humans do. A large sperm whale holds around 500 gallons of blood. Picture a typical water tank used to supply a small house and fill it entirely with blood. That is the sperm whale's internal supply. Blood carries oxygen. More blood means more oxygen stored. But the blood itself is also different. Sperm whale blood contains a much higher concentration of hemoglobin than human blood. Hemoglobin is the protein inside red blood cells that grabs oxygen molecules and holds them. More hemoglobin means more oxygen packed into every gallon of blood. So the whale dives with an enormous internal oxygen reservoir that human blood simply cannot match in volume or concentration. And the blood is only part of the system. As the whale descends and the body shifts into deep dive mode, blood flow changes throughout the body. Circulation to the muscles, skin, and most organs slows down or stops. The heart rate drops dramatically. The whale is essentially shutting off the parts of its body that are not immediately necessary and redirecting all remaining oxygen to the brain and the heart, the 2 organs that cannot survive even brief oxygen loss. This is called the dive reflex. Humans have a weak version of it. When you splash cold water on your face, your heart rate drops slightly. In a sperm whale, this reflex is extreme and precise. The body locks down everything non-essential and runs on minimum power, the way a phone switches to low battery mode and turns off every background function to preserve the core. But even with all that blood, all that hemoglobin, and the reduced circulation, 90 minutes is still an extraordinary amount of time. The blood alone does not explain it. There is a second oxygen storage system inside the whale's muscles, and it works on a completely different mechanism. It is so dense, so saturated, that it changes the colour of the whale's meat entirely. And that system is stranger than the blood. 500 gallons of blood. That number sounds impressive until you realise blood is only the first half of the whale's oxygen storage system. The second half lives inside every muscle in the whale's body, and it works in a completely different way. Muscles need oxygen to move. In most animals, including humans, muscles get their oxygen delivered by blood flowing through them continuously. Stop the blood flow, and the muscles fail quickly. A human arm with a tourniquet cutting off blood supply starts losing function within minutes, but during a deep dive, the sperm whale deliberately reduces blood flow to most of its muscles. Circulation slows. The blood supply that muscles normally depend on gets partially cut off, and the muscles keep working. This is possible because of a protein called myoglobin. Myoglobin is similar to hemoglobin, the oxygen-carrying protein in blood, but it lives directly inside muscle cells. Instead of carrying oxygen through the bloodstream, myoglobin stores oxygen inside the muscle tissue itself. When the blood supply drops, the muscle pulls oxygen directly from its own myoglobin reserve and keeps contracting. In humans, myoglobin is present in muscles but at low concentrations. That is why human muscles can only work for a short time without fresh blood flow before they cramp and stop. In sperm whales, myoglobin concentrations are extraordinarily high, so high that the protein changes the physical colour of the tissue. Human muscle is pinkish red. Sperm whale muscle is almost black. The difference in colour comes entirely from myoglobin density. The more myoglobin packed into a muscle cell, the darker it gets. Sperm whale meat looks like it has been burned. That dark, dense colour is the visible proof of how much oxygen each muscle cell can hold independently, without any blood supply at all. So here is how the full system works on a single dive. The whale takes one breath at the surface. The oxygen from that breath loads into the blood and into the muscle tissue. The whale dives. As pressure increases, the lungs compress and shut down. Blood circulation to non-essential parts of the body drops. The heart rate slows. The whale runs on stored oxygen, pulling from the blood and from the myoglobin in the muscles simultaneously. The result is a diving window of up to 90 minutes before the oxygen reserves run out. But even with all of that oxygen storage, the brain is the most fragile part of any animal. It runs on a tighter supply than muscles do. It cannot tolerate even a short drop in oxygen without damage. And during a 90-minute dive with reduced circulation, the brain still needs a steady protected supply that the standard blood system cannot guarantee on its own. So the whale has a third system, a hidden blood reservoir built specifically to protect the brain when everything else is running low. It is tucked inside the whale's body near the spine, and most people have never heard of it. The sperm whale's muscle looks nothing like meat you have ever seen in a grocery store. It is almost completely black. Not dark red, the way beef or venison looks. Black. The kind of colour that makes you think something went wrong, that the tissue is dead or burned. If you did not know what you were looking at, you would assume it was spoiled. The colour comes from myoglobin, and the amount of myoglobin packed into sperm whale muscle is so extreme it changes the fundamental appearance of the tissue at a level visible to the naked eye. Here is a way to picture the difference. Think of myoglobin like a set of lockers in a school hallway. In a human, each locker holds maybe 1 or 2 oxygen molecules. In a sperm whale, every locker is packed floor to ceiling. The hallway is longer, there are more lockers, and every single one is full. When scientists measure the myoglobin concentration in sperm whale muscle and compare it to a land mammal, the numbers are staggering. A typical land mammal has around 2 to 4 milligrams of myoglobin per gram of muscle. The sperm whale carries concentrations many times higher than that. The muscle is physically saturated with the protein. This has another effect beyond just oxygen storage. Myoglobin also buffers acidity inside muscle cells. During intense exercise, muscles produce acid as a byproduct of burning energy. That acid buildup is what causes the burning sensation in human muscles during hard physical effort. Too much acid, and the muscle shuts down. High myoglobin levels help neutralize that acid buildup, allowing the sperm whale's muscles to keep working longer and harder before fatigue forces them to stop. The whale can pursue, wrestle, and overpower prey at extreme depth without its own muscles failing from exhaustion. This combination, maximum oxygen storage plus acid resistance, makes sperm whale muscle one of the most efficient biological machines for sustained work under pressure ever found in nature. And the whale built all of this without anyone designing it. It emerged over millions of years of diving deeper and deeper, each generation slightly better equipped than the last, until the animal became what it is today. But storing oxygen in muscle solves one problem. The muscles can keep working. There is still the brain to protect. Brain tissue is far more sensitive than muscle. Muscles can tolerate some oxygen shortage. The brain cannot. Even a few minutes of reduced oxygen causes permanent damage in most animals. During a 90-minute dive with drastically slowed circulation, the whale's brain needs its own dedicated oxygen supply. A guaranteed line of blood that does not get shut down the way blood flow to the muscles and skin does. That supply comes from a structure most people have never heard of. A net of blood vessels woven around the spinal cord, acting as a private oxygen bank that feeds the brain alone. Scientists gave it a name in Latin. The name roughly translates to wonderful net. And it earns that name. Deep inside the sperm whale's body, wrapped around the base of the spine and woven through the chest cavity, sits one of the most remarkable structures in the animal kingdom. It is called the retia mirabilia. The name is Latin, and it translates directly to wonderful net. Scientists named it that because of what it looks like under examination, a dense, tangled web of blood vessels, looped and folded back on themselves in a complex mesh that stores a significant volume of oxygenated blood in reserve. Think of it like a battery backup for the brain. During normal activity at the surface, the retia mirabilia sits quietly, filled with oxygenated blood, waiting. When the whale dives and begins shutting down blood flow to most of its body, this structure does the opposite. It holds onto its oxygen supply and feeds it slowly, steadily, to the brain and spinal cord. The brain is the most oxygen-hungry organ in any animal. It burns through oxygen faster than muscle does, and unlike muscle, it cannot switch to a backup fuel source. If the brain loses oxygen for more than a few minutes, cells begin dying. The damage is permanent and fast. The retia mirabilia solves this by functioning as a dedicated protected blood reserve. Even as circulation to the rest of the body slows to a crawl, blood from this net keeps flowing to the brain. The whale's muscles may be running almost entirely on stored myoglobin during the deepest part of a dive, but the brain gets its own supply from the net, separated from the rest of the circulatory system. This structure appears in various forms across several marine mammals, including dolphins and seals. But in the sperm whale, which dives deeper and longer than almost any other air-breathing animal on Earth, the retia mirabilia is especially large and elaborate. Scientists studying it have described it as a pressure equalizer too. As the whale descends and blood pressure changes throughout the body, the retia mirabilia absorbs and buffers those shifts, helping to protect the delicate blood vessels in the brain from sudden pressure spikes that could cause internal bleeding. So the brain gets 2 layers of protection in a single structure: oxygen reserve and pressure buffering. The whale did not evolve this system for elegance. It evolved it because every dive was a test. The animals that could protect their brains longest during a deep dive caught more food, survived longer, and passed their traits to the next generation. After millions of years of that pressure, the result is a biological engineering solution that still impresses researchers today. Now the whale has its oxygen handled. The lungs compress and the system shifts to stored reserves. The brain gets protected. The muscles keep firing. But here is what nobody talks about. The whale still has to navigate down there. At 6,000 feet, there is no light. Zero, the human eye, even fully adapted to darkness, cannot detect a single photon at that depth. The whale cannot see its prey. It cannot see the walls of an underwater canyon. It cannot see anything at all, and yet it hunts with pinpoint accuracy in total blackness. What it uses instead of eyes is something far more powerful. 90 minutes. Sit with that number for a second. 90 minutes is a full-length film. A standard school class period. A trip from one side of a city to the other in traffic. The sperm whale holds its breath for all of that. While actively hunting, while chasing prey through total darkness at extreme depth. The human record for a static breath hold, a trained free diver lying completely still in calm water with every possible advantage, sits around 24 minutes. That person is doing nothing but lying there, conserving every molecule of oxygen in their body. The sperm whale is moving, pursuing, attacking, and returning to the surface, all on one breath held 3 to 4 times longer than the best human has ever managed. How is that possible given everything we have already covered? It comes down to integration. The flexible ribcage, the compressed lungs, the massive blood volume, the myoglobin-saturated muscle, and the retia mirabilia protecting the brain all work together as one coordinated system. None of them alone would be enough. Together, they create a machine built for one specific purpose: stay down, hunt, come back up. The dive itself follows a pattern. At the surface, the whale breathes rapidly, cycling air through its lungs and loading up oxygen stores in both blood and muscle. Scientists who have tracked this pre-dive breathing say it can last anywhere from 8 to 10 minutes. The whale is not just catching its breath, it is filling every storage system it has. Then it tilts headfirst and drops. The descent is fast. The whale actively swims downward at first, then gravity assists as the compressed lungs reduce buoyancy and the body becomes slightly denser than the water around it. It essentially starts to fall. Scientists tracking dive data from tagged sperm whales have recorded descent speeds of roughly 8 feet per second during the steepest part of the dive. At the bottom of the dive, the whale levels out and hunts. This active hunting phase can last anywhere from 20 minutes to over an hour, depending on prey availability. The whale is ranging across the deep, firing echolocation clicks, tracking prey, and maneuvering in total darkness. Then the ascent begins. And the ascent is where things get dangerous. Coming up too fast is deadly. The dissolved gases in the body need time to leave the bloodstream safely as pressure decreases. Ascend too quickly, and those gases come out of solution as bubbles. The same mechanism that causes the bends in human divers. The whale manages this by ascending more slowly than it descended. Scientists have observed that tagged sperm whales consistently slow their ascent rate in the upper portions of the water column, exactly where pressure changes most dramatically. The whale does this without instruction, without a dive computer, without decades of scientific research telling it when to slow down. It learned from millions of years of trial and error. But here is the thing. The system is not perfect. Something out in the modern ocean is forcing some whales to break their careful ascent pattern, and the damage it leaves behind is only visible in the bones of old whales. For a long time, scientists assumed sperm whales were immune to the bends. The logic made sense. They evolved to dive deep. Their lungs compress and shut down before nitrogen can dissolve into the blood. Their ascent is controlled and slow. The whole system looks like a perfect solution to the problem that kills human divers. Then scientists started examining sperm whale skeletons more carefully. What they found changed the picture. In the bones of older sperm whales, particularly in the large joints of the spine, scientists discovered a specific type of damage called avascular necrosis, which means bone tissue that has died because its blood supply was cut off. In human divers, this same damage is a known consequence of repeated decompression sickness events over a career. The pattern in whale bones told a story. Younger whales showed clean, healthy bone structure. Older whales, those that had spent decades diving, carried scattered patches of dead tissue in their skeletons. The damage was not from one catastrophic event. It was accumulated over years, one dive at a time. This meant the whale's system was mostly effective, but never perfectly immune. Small amounts of nitrogen were still making it into the bloodstream on some dives. Over decades, those tiny repeated exposures left permanent marks on the bones. Think of it like a car engine running slightly too hot. Each individual trip seems fine. The engine does not blow up. But over thousands of miles, the small repeated stress accumulates as wear that eventually shows up in ways mechanics can measure. The whale carries that wear in its skeleton. But the older whales with this chronic low-level damage are still diving, still hunting. The damage slows them down over time, but it does not stop them. What does seem to stop them, or at least cause acute injury, is something humans introduced to the ocean. Military sonar and seismic air guns used in ocean floor surveys both produce extremely loud, sudden sounds underwater. Researchers found that when whales are exposed to these sounds during a dive, some of them change their behavior in ways that are dangerous. Specifically, some whales that hear these sounds ascend faster than they should. A whale that panics and shoots toward the surface from 6,000 feet disrupts the careful, controlled decompression that keeps nitrogen in check. The sudden drop in pressure allows dissolved gas to come out of solution too quickly. Bubbles form in the bloodstream and joints. The result is acute decompression sickness in an animal that spent millions of years evolving to avoid exactly that. Scientists have found stranded whales following naval sonar exercises showing hemorrhaging consistent with rapid decompression. The whale's own finely tuned system, the one that works perfectly under natural conditions, gets short-circuited by sounds loud enough to cause panic. This raises a question about the role of sound in the sperm whale's world, because sound is everything to this animal. Sound is how it sees. Sound is how it hunts. Sound is how it communicates across hundreds of miles of open ocean. And the sounds a sperm whale makes on its own are unlike anything else in nature. The sperm whale's dive system is elegant. It took millions of years to build, and it works within tight biological limits. The controlled ascent. The slow decompression. The lungs compressed before nitrogen can enter the blood. Every piece depends on the whale following the right pattern, at the right speed, without disruption. One loud sound in the wrong place can break all of it. In the 1990s, navies around the world began deploying mid-frequency active sonar systems on warships and submarines. These systems work by sending out powerful pulses of sound underwater and listening for the echo to detect submarines and other objects. The pulses are not subtle. They are designed to travel vast distances through water, which means they carry enormous energy. Underwater, sound travels about 4 times faster than in air, and it does not lose energy the same way. A loud sound in the ocean can carry for hundreds of miles. When research vessels and Navy ships operate near areas where sperm whales are diving, those sonar pulses reach the whales at depth. What happens next has been documented in strandings on beaches across the world. Whales surface in groups. They are disoriented. Some are bleeding from their ears. Some die within hours. Autopsies on these animals reveal hemorrhaging around the brain and ears, gas bubbles in the organs, and bone damage consistent with fast decompression. The current understanding is that the sonar pulses cause panic. The whale, which has evolved over millions of years to respond to sudden loud sounds by moving quickly, responds the only way its instincts know. It tries to surface. Fast, but fast is the one thing the system cannot survive. A whale that ascends from 6,000 feet at maximum speed, the way it might if chasing prey near the surface, does not give nitrogen time to leave the bloodstream safely. The pressure drops too fast. Gas comes out of solution. Bubbles form in the blood, the joints, and around the organs. Seismic air guns present a similar threat. These are arrays of pressurized air cannons towed behind ships during ocean floor surveys for oil and gas deposits. They fire simultaneously, sending pulses of compressed air downward into the seabed that reflect off different rock layers and map the geology below. The sound these guns produce is among the loudest human-made sounds in the ocean. A single firing can produce sound levels comparable to an explosion, and survey ships fire them repeatedly for weeks at a time. Sperm whales in areas near seismic surveys have been observed changing their behaviour. They dive less deep, return to the surface more often, and in some cases abandon feeding areas they have used for generations. For an animal that already walks a biological tightrope every single dive, any disruption to its behaviour at depth has consequences. The whale built the perfect system over millions of years. We have had the power to disrupt it for about 50. And the irony is that humans use sound underwater for the same reason the sperm whale does. To see what is down there. The dive down is mostly physics. The whale swims hard for the first few hundred feet. Then the compressed lungs remove buoyancy, the body becomes denser than the surrounding water, and gravity does the rest. The whale essentially falls into the deep. Coming back up is a completely different challenge. The ascent requires calculation that the whale performs instinctively, adjusted by millions of years of evolution. Go up too fast, and nitrogen dissolved in the blood comes out of solution as bubbles. Those bubbles cause internal damage, pain, and sometimes death. Go up at the right rate, and the decreasing pressure allows nitrogen to leave the bloodstream slowly and safely through the lungs once breathing resumes. Scientists who attached data recorders to wild sperm whales have been able to map their dive profiles in detail. The recordings show a consistent pattern. Descent is fast, sometimes exceeding 8 feet per second at the steepest point. The active hunting phase at the bottom lasts anywhere from 20 minutes to over an hour. Then the ascent begins, and here is where it gets precise. In the deepest section, below around 1,000 feet, the whale rises at a moderate rate. But as it enters the upper portion of the water column, closer to the surface where pressure changes most rapidly for each foot of depth, the ascent rate slows measurably. The whale is throttling back exactly where the risk is highest. At 33 feet of depth, pressure is twice what it is at the surface. At 66 feet, it is 3 times. Every foot gained in that upper zone represents a larger percentage drop in pressure than the same foot at greater depth. If nitrogen is going to come out of solution as bubbles, it will happen fastest in this zone. The whale slows down here on its own. No dive computer. No training from a certified instructor. Just a biological instinct that precisely mirrors the safety stops human technical divers learned through decades of trial, error, and fatalities. Humans figured out decompression stops in the early 20th century after watching divers die from the bends. We turned that knowledge into tables and dive computers. It took us decades to get the math right. The sperm whale solved the same problem through evolution, with a margin of safety built into the behaviour of every individual animal. And even with that careful ascent, the wear still accumulates in the oldest bones. There is one more wrinkle in the ascent story. Young sperm whales, in their first years of diving, do not always follow the controlled ascent pattern that adults use. Their instincts are less refined. Their bodies are still building the full depth of biological adaptations that adults carry. Scientists believe this may be why younger whales, when they do strand, sometimes show more acute decompression damage than adults in similar situations. The system improves with age. The whale gets better at surviving as it gets older, accumulating wear but also accumulating precision. But even the most experienced, perfectly calibrated adult whale faces a problem when it reaches its hunting depth. It cannot see anything. Not a trace of light reaches 6,000 feet. The whale's eyes, functional and sharp at the surface, are useless at depth. So the whale sees with sound instead. 6,000 feet below the ocean surface, close your eyes. Now understand that opening them would make no difference. No sunlight reaches that depth. The surface of the ocean filters light as it passes through water. Red wavelengths disappear within the first 30 feet. Orange and yellow fade out by 100 feet. Blue and green light carries a bit further, but by 600 feet, even those are gone. At 6,000 feet, the ocean is in what scientists call aphotic, meaning no light whatsoever. A human eye at that depth, fully dark, adapted and operating at peak sensitivity, could not detect a single photon. The darkness is physically complete. For reference, the deepest, most recreational scuba divers go is around 100 feet, where colours are already muted and faded. Cave divers with specialised equipment push to around 300 feet. The military record for open circuit diving sits just below 2,000 feet, achieved once under extreme controlled conditions. The sperm whale routinely descends 3 times below that. In that darkness, everything the whale knows about hunting through vision becomes useless. Eyes require light. No light, no vision. It does not matter how good the whale's eyesight is at the surface. At depth, eyes are the wrong tool entirely. Every other animal in that zone faces the same problem. The giant squid, which has the largest eyes of any living animal, eyes roughly the size of a dinner plate, evolved those eyes partly to detect the faint bioluminescent flashes produced by other creatures in the deep. Even the giant squid, with eyes optimized for detecting the absolute minimum of light, is working at the edge of what biology can do with photons. At 6,000 feet, even the giant squid's vision is marginal. The sperm whale bypassed the problem entirely. Instead of trying to improve its eyes for a lightless environment, the whale evolved a completely different sense. One that does not need light at all. One that works better in water than it ever could in air, because water conducts sound far more efficiently than air does. The whale sees with sound. The system it uses is called echolocation, and the sperm whale version of it is the most powerful biological sound system ever discovered. It works by sending out a pulse of sound, waiting for that pulse to reflect off objects and return as an echo, and then using the timing, direction and character of that echo to build a detailed picture of the surrounding environment. Bats use a version of the same system. Dolphins use it too. But the sperm whale operates at a scale that makes those other versions look small. The sounds a sperm whale produces at depth are physically louder than any other biological sound ever recorded. And the structure inside the whale's body that generates those sounds is one of the strangest organs in the animal kingdom. The click happens in less than a millisecond. A burst of sound fires forward from the whale's massive head, travels through 6,000 feet of cold black water, bounces off a 40-foot squid hiding in the dark, and returns to the whale carrying precise information about the size, distance, texture, and movement of its target. This is echolocation. And in the sperm whale's hands, or rather its head, it becomes something extraordinary. Echolocation as a concept is simple. Send sound, receive echo, calculate what is out there. Bats do it to catch moths in the dark. Dolphins do it to track fish in murky water. The principle has existed in the animal kingdom for tens of millions of years. But the scale, power and precision of the sperm whale version put it in a different category. A bat echolocates at distances of maybe 30 to 60 feet. A bottlenose dolphin can detect a tennis ball-sized object from about 200 feet away. The sperm whale can detect prey from distances estimated at over a mile in some conditions. 1 mile. In complete darkness. Through water. The system works because sound travels exceptionally well in water. Water is denser than air, and that density allows sound waves to travel roughly 4 times faster and with far less energy loss. A sound pulse sent into open water retains more of its original energy over distance than the same pulse sent through air. The sperm whale takes advantage of this by producing clicks of extraordinary volume and precision. The clicks travel outward through the dark water, strike any solid object in their path, and bounce back as echoes. The whale's brain processes those returning echoes at a speed and precision that allows it to construct a 3-dimensional sound map of everything around it. The detail in that map is remarkable. Scientists believe sperm whales can distinguish between objects of different sizes, different materials, and different shapes based on how sound reflects from them. They can likely detect whether a potential prey animal is swimming toward them or away. They can probably sense depth, the distance of an object below or above them, with high accuracy. All of this in total darkness. All of this at 60 atmospheres of pressure. All of this while managing a 90-minute oxygen budget. The clicks themselves are directional. They do not spread equally in all directions like ripples from a stone dropped in water. They fire forward in a focused beam, concentrated toward the target. This focusing is what allows the system to work at long range. A dispersed sound loses energy quickly. A focused beam carries further and returns a sharper echo. The focusing happens inside the whale's head, specifically inside a large organ filled with oil that sits in the front of the whale's enormous skull. That oil has been studied for centuries. Whalers prized it so highly that entire industries were built around harvesting it. But what that oil actually does inside a living, diving, hunting whale is a question scientists are still working through today. The sound does not come from the throat. The sperm whale produces its clicks through a system entirely unique in the animal kingdom. No vocal cords, no larynx. The clicks are generated by a pair of specialized structures near the front of the whale's head called phonic lips. Phonic lips are small, dense tissue structures that sit just inside the blowhole passage at the top front of the skull. When air is forced through them from an internal air sac behind the skull, they snap together rapidly. That snap is the click. The sound produced by that snap is intense, directional, and extraordinarily loud. The click fires into the front of the whale's head and enters a large oil-filled organ called the spermaceti organ. This organ sits in the upper portion of the whale's rectangular head and can account for a massive fraction of the head's total volume. In large adult males, the entire head, which is already 1/3 of the body, is largely taken up by this structure. The oil inside the spermaceti organ has unusual acoustic properties. It is denser and more uniform than seawater, which makes it an effective medium for shaping and directing sound waves. Scientists believe the spermaceti organ acts like an acoustic lens, focusing the click into a tighter, more coherent beam before it exits the head and travels into the water. Behind the spermaceti organ, at the base of the skull, sits a concave, air-filled sac called the museau du singe, which French whalers named centuries ago, meaning monkey's muzzle for its shape. When the forward-travelling click reaches this sac, it reflects back forward. The reflected pulse travels through the spermaceti organ a second time and exits with even more focused directionality. A second oil-filled structure called the junk sits in front of the spermaceti organ. The junk is made of alternating layers of oil-saturated tissue and connective material, stacked like a series of acoustic lenses, each layer further shaping and concentrating the sound as it passes through. The result is a click that exits the front of the whale's head in a narrow, powerful forward beam. The entire system works together as a biological acoustic device of remarkable precision. The phonic lips generate the raw sound, the spermaceti organ shapes it. The reflecting sac behind the skull bounces it forward for a second pass. The junk focuses it into a beam. Engineers designing underwater sonar systems essentially work toward the same goals using metal, electronics, and software. The sperm whale achieves comparable results using oil, tissue, and air sacs, and the volume this system produces is something no human technology has ever matched in a biological context. The click that exits that head is the loudest sound ever recorded from any living animal on Earth. Not slightly louder, dramatically louder. The number that measures it seems almost impossible until you start comparing it to things you actually know. The loudest thing most people have ever stood near is probably a concert speaker stack or a motorcycle engine. Those run somewhere between 100 and 110 decibels. Painful after extended exposure. Capable of causing permanent hearing damage with repeated contact. A gunshot fired close to an unprotected ear measures around 150 decibels. Exposure for even a fraction of a second can permanently damage hearing. A jet engine at full takeoff thrust, standing on the runway, measures around 150 decibels in air. A sperm whale click, recorded underwater, reaches 236 decibels. That number requires context, because the decibel scale is not linear, it is logarithmic. Every 10 decibels represents roughly 10 times the acoustic intensity. So the difference between 150 decibels and 200 decibels is enormous, and 236 is higher still. To put it another way, a single sperm whale click, measured underwater, carries more acoustic energy than a jet engine on a runway. One click. 1 millisecond. More energy than a machine that burns thousands of gallons of fuel per hour and produces enough thrust to lift a 400,000-pound aircraft off the ground. A direct comparison to familiar sounds is tricky because decibels in water and decibels in air use different reference points. Sound travels differently in each medium, but researchers who have done the conversion estimate that a sperm whale click heard at close range would be roughly equivalent in destructive power to hundreds of rifles firing simultaneously. A single sperm whale click is approximately 4 times louder than a thunderclap to the human ear. Standing next to a speaker producing that volume, if such a speaker existed, would cause instant, permanent, total hearing loss. At close range, the pressure waves alone could cause internal injury. The whale fires these clicks continuously during a hunt, dozens per minute. And here is what makes this even stranger. The whale's own brain and hearing system survive this without damage. The physical structures around the phonic lips and spermaceti organ are built to handle the energy the system produces. The whale is essentially firing a weapon from inside its own skull, repeatedly, and its internal architecture absorbs the output without injury. Now consider the squid being hunted. A 40-foot animal with a soft fluid-filled body is receiving those clicks from a closing distance. The acoustic energy washing over it is significant. And this is where scientists began asking an uncomfortable question. What if the clicks do more than locate the squid? What if they are also designed to hurt it? The number 236 decibels lives in a range most people have never encountered and cannot directly imagine. So let us build up to it from things you actually know. A whisper in a quiet room sits at around 30 decibels. Quiet, barely there. Normal conversation registers around 60 decibels, 10 times more intense than that whisper, by the math of the logarithmic scale. A lawnmower running next to you hits around 90 decibels. Uncomfortable after an hour. A rock concert at the front row reaches around 110 decibels. Most venues have to keep speakers below 115 to avoid violating noise regulations. A gunshot next to an unprotected ear, 150 decibels. Instant damage. Even brief exposure can permanently shift your hearing threshold. A military jet at takeoff, standing on the runway, matches that number. Now add another 86 decibels on top of that, 236 decibels. The acoustic intensity at that level in water is so extreme that the physics of what sound can do to living tissue changes entirely. Sound at high enough intensity does not just stimulate the ear, it moves matter. It generates pressure waves powerful enough to physically compress and expand the tissues of a living body in rapid succession. Scientists use focused ultrasound in hospitals to break apart kidney stones without surgery. That process works by directing concentrated sound energy at a hard object until the pressure cycles shatter it. The sound levels used in medical ultrasound are a fraction of what a sperm whale produces. What a sperm whale click does to any soft-bodied animal caught in the direct forward beam at close range is something researchers have genuinely debated. A team of scientists once attempted to test whether high-intensity sound at frequencies comparable to sperm whale clicks could physically stun a squid. They built an underwater acoustic array capable of producing the relevant frequencies and exposed squid to the sound in controlled conditions. The results were not what the acoustic weapon theory predicted. The squid in the experiment were not paralyzed. Some showed stress responses, some moved away from the sound source, but none were incapacitated in the dramatic way the hypothesis suggested. This does not prove the clicks have no physical effect on prey in real conditions. It proves the lab setting could not replicate what happens during an actual hunt in the deep ocean. In the real hunt, the whale is not stationary. It is closing distance rapidly. The squid is in open water with nowhere to hide. The geometry of the encounter, the angle, the range, the duration of exposure, differs enormously from a lab tank. And the squid is a formidable animal in its own right. 40 feet of muscle, armed with serrated suckers, capable of moving at speed in any direction. Whatever happens in that dark, crushing water, it leaves marks on both animals. The whale comes back with scars. The squid does not always come back at all. The idea started with the scars. Scientists examining sperm whales at the surface kept noticing the same thing. Circular marks pressed into the skin, sometimes covering large sections of the body. Rings of raised scar tissue that matched the diameter of giant squid suckers almost exactly. The whale was winning these encounters. It had to be, because it was returning to the surface alive and full. But the marks told a story of something that fought back hard. A 40-foot squid in total darkness at 6,000 feet of depth, with no room to flee and a predator closing in, is not a passive meal. It is an animal built for combat, with 8 arms, 2 long feeding tentacles, and suckers lined with sharp serrated rings capable of cutting through flesh. Scientists began asking how the whale was subduing something that large, that strong, and that armed, in complete darkness, without being able to see it. The anatomy provided one possible answer. The sperm whale's forward-firing click system produces sound at pressures so extreme that researchers began wondering whether the acoustic energy itself could be used offensively. The hypothesis became known as the acoustic stun theory. The idea was that at close range, the whale's echolocation clicks might be powerful enough to physically disorient or temporarily disable the squid, making capture easier. The logic had some physical grounding. High-intensity sound pressure waves can cause disruption in soft tissue and fluid-filled cavities. A squid's body is soft, fluid-filled, and has no hard shell to absorb or deflect pressure waves. If anything biological is vulnerable to concentrated acoustic energy, a large squid is a reasonable candidate. A sperm whale producing 236 decibels of directional sound pointed directly at a squid at close range while closing the distance rapidly generates a scenario where the acoustic energy reaching the target is significant. Researchers also pointed to behaviour. Sperm whales do not simply ram into prey. They approach, they click, they manoeuvre. The clicking intensifies before a capture. Sound output increases precisely in the moments before the whale closes in. Some scientists interpreted this as the whale using sound not just to locate the squid, but to prepare it for capture, possibly disorienting it, possibly stunning the statoreceptors in the squid's body that control balance and orientation. A disoriented squid that cannot track which way is up or respond quickly to the approaching whale would be far easier to swallow. The theory was compelling enough that research teams began designing experiments to test it. And what they found complicated the picture considerably. The squid did not go down the way the theory predicted. But the experiments also revealed something important about what we actually know versus what we assume about a hunt that has never been directly observed. Nobody has ever watched a live sperm whale hunt a giant squid at depth. Every piece of evidence comes from scars, from stomach contents, from acoustic recordings, and from behaviour observed at the surface. What actually happens in the 6,000 feet of darkness below is still, in meaningful ways, unknown, and the animal the whale is hunting is stranger than most people realise. The experiment was designed carefully. A team of researchers built an underwater acoustic system capable of producing high-intensity sound pulses at frequencies similar to those recorded from hunting sperm whales. They placed squid in a controlled tank environment and exposed them to the sound. The squid did not freeze. Some swam away from the sound source. Some showed elevated activity, moving more than usual. A few appeared stressed by the exposure. But none of them were paralysed, none lost coordination, and none became easy to catch in the way the acoustic stun theory predicted. The researchers published their findings and noted that the hypothesis remained unproven. This created a problem for the theory, but it did not kill it entirely. And here is why. The conditions in a tank are fundamentally different from the conditions in the deep ocean during an actual hunt. In a tank, the squid has walls around it. The sound reflects off those walls and creates interference patterns that change how the energy reaches the animal. The squid is not being approached at speed by an animal closing the distance from one direction. The geometry is completely different. The whale in a natural hunt is moving. The click is directed forward. The squid is receiving an increasing intensity of sound from a single direction while a predator closes in behind that sound. The duration of exposure, the directionality, and the rate at which intensity increases as the whale approaches are all variables the tank experiment could not replicate. Scientists who study bioacoustics, the study of how living things use and respond to sound, point out that the effect of intense directional sound on squid at close range in open water remains genuinely unknown. The lab result rules out one version of the stun theory, the idea that sound alone at relevant frequencies reliably paralyzes squid under any condition. It does not rule out the possibility that acoustic energy plays a role in close-range encounters under specific conditions. There is also the question of the statocysts, which are fluid-filled balance organs in the squid's body that detect gravity and movement. These structures are soft and fluid-filled, making them theoretically susceptible to pressure waves. Some researchers believe that disrupting the statocysts, even temporarily, could cause disorientation sufficient to make capture easier without outright paralysis. That specific question has not been fully tested. So the acoustic weapon theory sits in a complicated place. The strongest version of it, Click's reliably stun squid, is unsupported by current evidence. The weaker version, sound may play some role in the capture beyond simple location, remains an open question. What the evidence does confirm is this: the hunt works. The whale catches the squid, and the squid fights back every time. The scars prove it. 40 feet of muscle, reaching out from a darkness so complete that no camera has ever filmed what happens down there between predator and prey. The giant squid is the whale's primary target, the reason it descends past 6,000 feet repeatedly for its entire life. And the squid earns the whale's effort. A fully grown giant squid can stretch 40 feet from the tip of its mantle, the main body section, to the end of its two long feeding tentacles. Its mantle alone can be 6 feet long. The body is mostly water and soft tissue, which is why it collapses to an unimpressive mass when stranded or dead. Alive in the deep, it is a completely different thing. The squid moves using jet propulsion, drawing water into its mantle and expelling it in a powerful burst. In the open ocean, this makes it highly maneuverable and fast in short bursts. It can move in any direction, including backward, faster than most animals its size can respond. Its 8 arms are lined with suckers. Each sucker on the tentacles, the 2 longer arms used for catching prey, is ringed with a serrated chitin ring, a hard, sharp circle that acts like a circular saw blade when the tentacle grabs and twists. These rings do not just hold, they cut. When a giant squid grabs something, the tentacles wrap around it and the serrated suckers dig into the flesh. The grip is powerful and the cutting is automatic with any movement. Struggling against the grip makes the damage worse. The whale comes back from deep hunts with circular scar patterns pressed into its skin, rings of raised tissue from suckers that grabbed and held during the battle. Some whales carry these marks over large portions of their bodies. The encounters are clearly physical and extended. And the squid's own eyes are extraordinary. The giant squid has the largest eyes of any animal alive, up to 10 inches across, roughly the size of a dinner plate. Those eyes evolved specifically to detect the faint bioluminescent flashes produced by other creatures in the deep ocean, the brief lights that living things make when disturbed. Even in near total darkness, the giant squid can detect movement by the light that movement produces. The whale's clicks would likely cause some of the squid's bioluminescent responses to trigger, potentially revealing the squid's exact position even as it tries to evade. Neither animal has a clean advantage. The whale has sound, size and jaw suction powerful enough to swallow the squid whole. The squid has speed, grasping arms, serrated suckers, and the ability to eject a cloud of dark ink to confuse any predator that hunts by sight. Ink is useless against echolocation. The battle in the deep is a mismatch in some ways, and an even contest in others, and after the whale wins, which it mostly does, a different problem begins. Something inside the squid that the whale's stomach absolutely cannot digest. Every time a sperm whale surfaces after a deep hunt, its skin carries the record of what just happened. The circular marks are pressed into the flesh in patterns that scientists can read like a map of the battle below. Small rings mean smaller suckers, from younger or smaller squid. Larger rings, sometimes 3 or 4 inches across, come from mature giant squid tentacles. Overlapping patterns suggest the squid wrapped multiple tentacles around the whale during the encounter. Some whales carry these marks from their nose to their flanks. The density and distribution of scars on an individual whale's body can tell researchers roughly how many hunts it has been through, and how large its typical prey has been. The fresh wounds are visible as red, raw circles. Over time, they heal into raised, pale rings of scar tissue that remain visible for the rest of the whale's life. An old male sperm whale covered in scars is a whale that has hunted successfully hundreds of times. The scars are evidence of something specific. The squid was alive and fighting when the whale made contact. If the whale were simply swimming up to helpless prey, there would be no scars. The marks exist because the tentacles grabbed back. The suckers cut into the whale's skin during a struggle. Scientists studying the scar patterns have been able to draw conclusions about the nature of the encounters. The locations of scars around the whale's head and lower jaw suggest the squid targets the mouth area during defense, likely attempting to grab the jaws and prevent the whale from biting or sucking. Scars on the flanks and back suggest the squid sometimes wraps partially around the whale during the struggle. The whale's strategy appears to be suction capture. Get close enough to open the jaw and generate the inward pull that draws the squid into the mouth. The squid's strategy appears to be preventing that from happening by grappling with the attacker. Both strategies show up in the scarring. One detail from the scar record particularly interests researchers. The largest scars ever recorded on a sperm whale's skin came from sucker rings measuring over 4 inches in diameter, significantly larger than any living giant squid confirmed by science. Scientists have pulled sucker rings from whale stomachs that suggest prey animals well beyond the 40-foot maximum currently documented for the giant squid. Larger squid. Potentially much larger, living in depths humans have barely explored. The whale's scars point toward animals science has not yet confirmed exist. That is a remarkable thing for a scar to suggest. And the battle itself is only part of what makes the hunt costly. After capturing a giant squid, the whale faces a second problem, one hidden inside the squid's body that the whale has been solving quietly for millions of years, producing something so valuable it changed the history of human commerce. The sperm whale's lower jaw is one of the most misleading structures in the animal kingdom. It is narrow. Remarkably narrow for an animal this size. From the front, it looks almost comically thin compared to the enormous rectangular head above it. The jaw lines up along the bottom of the head like a single narrow plank attached to a building, and it is lined with large conical teeth. Each tooth is roughly the size and shape of a banana. A large adult male carries between 20 and 26 teeth along the lower jaw, all on one side, fitting into matching sockets in the upper jaw when the mouth closes. The upper jaw itself carries almost no functional teeth. The upper sockets exist, the holes are there, but in most sperm whales the upper teeth never fully erupt from the gum and play no role in feeding. The whale carries a full set of upper tooth sockets and almost never uses them. This puzzled researchers for a long time. What is the point of a predator with teeth on only one side of its mouth? The answer is that the teeth are largely secondary to the actual capture method. The sperm whale's primary hunting tool is suction. When the whale opens its long narrow jaw and drives toward prey, the geometry of that narrow jaw creates an efficient hydrodynamic channel. Water and prey rush inward along that channel as the mouth opens. Muscles in the throat contract powerfully, creating a suction effect strong enough to pull a large squid into the throat in a fraction of a second. The teeth then close over the prey to prevent it from escaping, but the capture itself happens through suction and momentum before the teeth play any role. Scientists have studied sperm whale stomachs and found large prey animals swallowed completely intact, with no bite marks. The suction system works well enough that the teeth sometimes do not contact the prey at all during capture. There is also evidence that the narrow lower jaw is part of the echolocation system. The jaw is filled with an oil-rich tissue called acoustic fat, which conducts sound efficiently. Some researchers believe the jaw acts as a receiving antenna for returning echolocation echoes, channeling sound back toward the inner ear. So the same jaw serves two purposes. It captures prey through suction and houses the acoustic receiver for the sonar system. The upper jaw, full of empty sockets, sits mostly unused above it. But the whale's head is full of structures, doing multiple things at once. And the largest and most mysterious of them sits right above the jaw, filling the enormous rectangular skull with an oil that whalers once considered worth more than gold. The upper jaw of a sperm whale is an anatomical mystery that took scientists decades to partially understand. Run your finger along the upper jaw of a large sperm whale skull and you find sockets. Dozens of them, evenly spaced, precisely formed, running the full length of the jaw. They look exactly like the sockets in any toothed predator's jaw, round openings in the bone, clearly designed to hold teeth, mostly empty. In the overwhelming majority of sperm whales examined, the upper teeth never fully emerge from the gum tissue. They develop below the surface, sometimes partially, sometimes as small rounded nubs, but they do not erupt into functional teeth. Some individuals show no upper teeth at all, and the whales feed successfully regardless. A predator that evolved perfect tooth sockets but stopped using the upper teeth is telling researchers something important about how its feeding strategy changed over its evolutionary history. The current understanding is that the sperm whale's ancestors were more conventionally toothed predators. Earlier relatives of the sperm whale used both upper and lower teeth to grab and hold prey. Over millions of years, as the suction feeding strategy became dominant and the jaw shape shifted to optimize for that method, the upper teeth became redundant. But evolution rarely eliminates structures quickly. Features that are no longer actively harmful tend to persist long after they stop being useful. The upper sockets remain because there was no strong pressure to remove them. They are vestigial, leftovers from an earlier design that the modern whale no longer needs. This is the same reason humans carry a small tailbone at the base of the spine. An ancestor used it. The modern version does not. But removing it entirely takes many more generations of pressure to accomplish. The empty upper sockets of the sperm whale are a fossil record written into a living animal's skull. They tell a story of a predator that gradually gave up biting and learned to vacuum its food instead. There is one specific case where the upper teeth do appear to serve a function. In battles with very large prey, some researchers believe the partially erupted upper teeth may help grip a struggling animal when suction alone is insufficient to hold it. But the main takeaway from the empty sockets is this. The sperm whale's hunting system changed so completely over its evolutionary history that it kept the housing but discarded the tool. The sockets sit empty. The jaw below them does all the work. And above the jaw, taking up an almost unbelievable fraction of the whale's head, sits a structure that whalers killed millions of whales to extract, that perfumers once paid fortunes for, and that scientists are still arguing about today. It is filled with oil, and nobody is completely sure what it is for. The sperm whale's head is enormous even by whale standards. In a large adult male, the head accounts for 1/3 of the animal's total length. A 60-foot whale carries a 20-foot head, and most of that head, the top section, the rectangular block that gives the animal its distinctive silhouette, is taken up by a single structure filled with a waxy yellowish oil. This is the spermaceti organ. When whalers first hunted sperm whales centuries ago, they discovered that the head contained a liquid that solidified into a white waxy material when it cooled. They misidentified it, believing it was a reproductive fluid. The name they gave the whale reflects that mistake. Spermaceti simply means sperm of the whale in Latin. It is not reproductive fluid. It is a dense, complex oil with unusual physical properties, and scientists have spent decades arguing about what it actually does for the living animal. The organ itself is large. In a big adult male, it can hold over 500 gallons of the oil. That is the equivalent of filling a small room with liquid. The oil is contained in a tough, fibrous case within the head, surrounded by a second oil-filled structure called the junk, which is layered with alternating sections of oil-soaked tissue. The sheer volume of the organ raises the first obvious question. Why would an animal dedicate that much of its body to a single structure? There are two leading theories. Each one proposes a completely different primary function, and the evidence for both is good enough that researchers cannot definitively choose between them. The first theory involves buoyancy. The sperm whale needs to descend to 6,000 feet and then return to the surface repeatedly for its entire life. Managing buoyancy, the balance between floating and sinking, is critical to making those dives efficient. Spermaceti oil changes density when it changes temperature. Warm oil is slightly less dense, creating upward buoyancy. Cool oil is slightly denser, making the head heavier. If the whale can heat and cool the oil in its head during a dive, it could potentially adjust its own buoyancy like a living submarine ballast tank. The second theory involves sound. The spermaceti organ sits directly in the path of the whale's echolocation clicks and appears to focus and direct them. Its acoustic properties suggest it could function as a biological lens for sound. Both theories are supported by evidence. Neither is proven as the primary function. And the two might not be competing. The same structure might do both things at once. The ocean asks a question of every diving animal. How do you go down efficiently, stay at depth, and come back up without burning all your energy just moving through the water column? For fish, the answer is a swim bladder, a small gas-filled sac that the fish inflates or deflates to adjust its position in the water without swimming. The swim bladder lets a fish hover at any depth by tuning its internal air volume until its overall density matches the water around it. The sperm whale has no swim bladder, but some researchers believe it has something better. Spermaceti oil behaves differently from most oils when temperature changes. It is unusually sensitive to heat and cold. Warm spermaceti is slightly less dense, making the head a little more buoyant. Cool spermaceti is slightly denser, making the head a little heavier. The change is subtle for any single degree of temperature shift, but the volume of oil in the whale's head is so large that even small density changes across hundreds of gallons produce meaningful buoyancy effects. The theory works like this. At the surface, the oil in the spermaceti organ is at body temperature, warm and slightly less dense. As the whale dives and begins drawing cold seawater through channels in the head, the oil cools and becomes denser. This makes the head heavier, which helps pull the whale downward and reduces the work its muscles have to do during descent. At depth, the whale can manage its position in the water column partly through this passive density adjustment rather than constant swimming. Then, as it prepares to ascend, the blood vessels around the spermaceti organ deliver warm blood to the oil, heating it back up, reducing density, and helping to lift the head toward the surface. Controlled sinking and floating, powered by the whale's own circulation rather than muscular effort. Researchers who support this theory point to the elaborate network of blood vessels around the spermaceti organ, vessels that could precisely regulate heat exchange. As evidence the structure is built for thermal control, skeptics point out that the density change from heating and cooling spermaceti is relatively small compared to the whale's total body weight and question whether it is large enough to matter meaningfully. The debate continues. But the buoyancy theory only covers one possible purpose. The second theory, involving sound, is supported by the anatomy of the click system we already covered. And what makes this genuinely strange is that both things might be true simultaneously. The same 500 gallons of oil might focus sound in one direction and manage buoyancy in another. Evolution does not require elegant solutions, it requires working ones, but the spermaceti is not the only product of the whale's deep hunting life that humans have found remarkable. Inside the gut, the squid creates a problem. And the whale's solution to that problem became one of the most valuable substances in the history of human trade. The click leaves the phonic lips as a raw burst of sound. Without any shaping, it would spread outward in all directions, losing energy rapidly and arriving at a distant target as a weak, dispersed wave too faint to return a useful echo. The whale cannot afford that. At 6,000 feet, hunting a fast-moving squid in total darkness, it needs a tight, focused beam that travels far and returns a sharp echo. The spermaceti organ, sitting directly in the path of the outgoing click, may solve this problem. Oil conducts sound differently than water or tissue. Its density and physical properties affect how sound waves move through it and how they behave at the boundaries where different materials meet. A carefully shaped body of oil can bend, channel, and focus sound in the same way a glass lens focuses light. The spermaceti organ's shape, its position relative to the phonic lips that generate the click, and its acoustic properties all align with what you would design if you wanted to focus a sound beam forward into the water. Sound entering the front of the organ from the phonic lips travels through the oil, reflects off the air-filled museau du songe sac at the rear of the skull, bounces forward again, and passes through the layered junk structure at the front of the head before exiting into the water. Each surface the sound encounters shapes it slightly. The oil focuses it. The rear reflector adds directionality. The junk layers do final shaping. What exits the head is a tighter, more coherent beam than what entered. The key evidence for the acoustic lens theory is the geometry. The structures in the sperm whale's head are arranged in a way that makes acoustic sense. The phonic lips are at the right position to fire into the organ. The rear reflector is at the right angle to bounce sound forward. The junk layers have the right physical structure to act as sequential acoustic shapers. Researchers who have built mathematical models of sound propagation through the sperm whale's head find that the structure does focus sound in the forward direction. What remains uncertain is whether this is the primary purpose the organ evolved for, or whether focusing sound is a byproduct of a structure that primarily evolved for buoyancy control. Some researchers argue both functions are real, that the spermaceti organ is a multitasking structure, and that it would be strange for an organ this large to do only one thing. The debate over spermaceti's primary function has been running for over 50 years. Meanwhile, inside the whale's stomach, a completely separate biological process was quietly producing something that shaped human civilization in a way nobody expected. A giant squid is mostly soft. The mantle, the tentacles, the suckers, all of it is protein-rich tissue that a sperm whale's digestive system handles without difficulty. The stomach acid breaks it down. The nutrients absorb. The meal becomes fuel. But inside every giant squid sits one hard, indestructible piece: the beak. Squid beaks are made of chitin, the same dense material that forms insect shells and crab claws. The beak is hard, sharp and curved, shaped roughly like a parrot's beak, and it serves the squid as a jaw. The squid uses it to bite through prey and tear off pieces small enough to swallow. When a sperm whale swallows a giant squid whole, everything dissolves except the beak. The beak resists the whale's digestive acid completely. It sits in the stomach, hard and sharp, pointed edges pressing against the soft lining of the gut. Multiple squid meals mean multiple beaks accumulating in the stomach over time. Some sperm whale stomachs have been found containing hundreds of squid beaks, hundreds of sharp, hard, indestructible objects sitting in the stomach of an animal that eats giant squid for decades. The whale's digestive system had to solve this problem. The solution it developed is one of the most unexpected materials in nature. The intestines of some sperm whales produce a waxy, fatty substance that coats the accumulated beaks over time. The substance builds up in layers around the sharp edges, encasing them in a softer, smoother material that prevents the beaks from cutting the gut lining. Over years, this material accumulates around a mass of beaks and compresses them into a dense, waxy solid. This solid, called ambergris, passes out of the whale eventually and floats in the ocean or washes ashore on beaches. It smells, when fresh, like the inside of a barnyard. Over time, exposed to sun and salt air, it develops a complex, earthy, musky scent that perfume makers discovered centuries ago could fix other fragrances, meaning it makes scents last longer on skin. Fresh ambergris smells terrible. Aged ambergris is worth thousands of dollars per pound. For centuries, people found strange waxy lumps washed up on beaches and had no idea where they came from. The substance was dense, pale grey or golden brown, and smelled unlike anything else in nature. Perfumers discovered that mixing it with other fragrant materials produced scents that lasted far longer on skin than anything else available. It became one of the most sought-after ingredients in the history of the fragrance industry. The source of ambergris stayed mysterious for a long time. It was sometimes called floating gold. Theories about its origin ranged from the secretion of seabirds to the product of ocean fungi. Some people believed it formed spontaneously from the sea itself. The answer, when scientists finally pieced it together, was the sperm whale's digestive system. Ambergris forms in the large intestine of some sperm whales, specifically around the accumulation of giant squid beaks that the stomach cannot break down. The intestinal wall produces a waxy secretion that coats these sharp objects, binding them together over time into a dense, solid mass. The mass grows over years. Some pieces of ambergris found at sea or on beaches are the size of a small car. The largest piece ever recorded weighed over 250 pounds and was found inside a whale. Once expelled by the whale, ambergris floats. The oils in it are less dense than seawater. It drifts on ocean currents for years, sometimes decades. Sun and salt water slowly change its chemistry during this time, breaking down the compounds that smell foul and leaving behind the complex, earthy molecules that perfumers prize. A fresh piece of ambergris found on a beach might be worth very little due to its unpleasant smell. A piece that has been drifting and curing in the ocean for 20 years could be worth tens of thousands of dollars. Today, major perfume houses mostly use synthetic substitutes for ambergris because the natural material is scarce, expensive, and because sperm whales are a protected species. But some luxury fragrances still use aged natural ambergris, and the market price for authenticated pieces remains extraordinarily high. The whale, solving a digestive problem caused by the sharp beaks of its prey, accidentally created one of the most commercially valuable natural substances in human history. Every piece of ambergris floating in the ocean today is the product of a whale hunting in darkness at 6,000 feet. And while the ambergris story is remarkable, there is something inside the whale's skull that dwarfs it in significance. Something that may be doing things we have barely started to understand. Inside the sperm whale's enormous skull sits the largest brain of any animal ever known to have existed on this planet. Not the largest relative to body size, the largest in absolute terms. Raw volume. Total weight. A mature sperm whale carries a brain that weighs around 18 pounds. A human brain weighs about 3 pounds. The sperm whale's brain is 6 times heavier. For comparison, a blue whale, which is a significantly larger animal, has a brain roughly the same size as a sperm whale's or slightly smaller. Size of body does not automatically mean size of brain. The sperm whale built something extraordinarily large relative to what the rest of its biology would predict. Why an animal needs a brain that large is a question researchers have spent decades on, without a clean answer. Some of it is the complexity of echolocation. Processing the acoustic information from returning clicks in real time, building a 3-dimensional map of a dark environment from echo timing and frequency, tracking moving prey while managing one's own position in 3 dimensions is computationally demanding. A bigger brain handles more of that processing simultaneously. But echolocation alone does not fully explain 18 pounds of brain. Sperm whales live in complex social groups. Females and young travel together in family units that can number over 20 individuals. These groups maintain long-term relationships. Older females appear to lead and make decisions for the group. Young males are raised within these units for years before leaving to range independently. Research into sperm whale communication has found that different groups have distinct click patterns, called coders, that function like a social identity marker. Groups from different parts of the ocean carry different coders. Calves learn their group's coder from the adults around them. Scientists studying these patterns have described the structure as resembling cultural transmission, the passing of learned behaviour from one generation to the next, similar in some ways to how human dialects spread through communities. The brain required to learn, maintain, and use these social codes across a lifetime of complex group relationships is a different kind of brain than the one needed simply to hunt squid. Researchers have also found evidence of long-term memory in sperm whales. Historical records from the era of commercial whaling document cases where whale groups appeared to alter their movement patterns in specific ways after hunting pressure intensified in an area. Behaviour consistent with learning and memory rather than pure instinct. Whatever the sperm whale is doing with 18 pounds of brain, it is doing more than the average predator, and when it is done doing it, it sleeps in a way no other large mammal does. When a sperm whale sleeps, it does not drift sideways in the water the way you might imagine a large marine animal resting. It hangs vertically. Head up or head down, the whale suspends itself in the water column like a pillar, completely motionless. Sometimes in a group of other whales doing exactly the same thing. A cluster of sperm whales sleeping in this posture looks like a forest of enormous posts floating upright in the open ocean. This behaviour was documented clearly in 2008, when a sailing vessel encountered a group of sperm whales floating vertically and motionless near the surface off the coast of Chile. The crew sailed carefully through the group without disturbing them. The whales did not respond. They were, by every measure, deeply asleep. The discovery was notable because it was the first documented observation of sperm whales sleeping in their natural environment, and the posture was completely unexpected. Why vertical? The answer likely connects to the sperm whale's respiratory biology. As an air-breathing animal, the sperm whale needs to surface regularly to breathe. Sleeping vertically near the surface allows the blowhole, positioned at the top of the head, to remain within easy reach of air. A whale sleeping horizontally at depth would have to actively swim upward each time it needed to breathe. Vertical suspension near the surface allows the whale to take a breath with minimal effort between sleep cycles, essentially hovering at a depth where the blowhole clears the surface during slow upward drift. Scientists studying the sleeping behaviour found that sperm whales appear to sleep in short cycles, entering the deepest sleep phase for around 10 to 15 minutes at a time. They surface, breathe, and re-enter the vertical rest posture. Total daily sleep time appears to be around 7% of the day, roughly 100 minutes spread across multiple short cycles. 7% of a day is far less sleep than most mammals need. Humans spend roughly 33% of their lives asleep. The sperm whale's reduced sleep requirement may relate to its lifestyle. Spending so much time at depth, in a state of reduced metabolic activity during dives, may provide a form of rest that reduces the total sleep debt the animal accumulates. The vertical sleeping posture also leaves the whale relatively defenseless. A sleeping sperm whale floating near the surface is not scanning for threats or monitoring its environment actively. The sailing crew that documented the 2008 encounter was able to move within feet of sleeping whales without triggering a response. For an apex predator, this is a vulnerability. Nothing in the modern ocean regularly hunts adult sperm whales. The only animal that poses a genuine threat to a healthy adult sperm whale is the orca, and even orca attacks on adults are rare. The whale's size and the damage it can inflict with its jaw make it a dangerous target. But at 6,000 feet, the whale is never truly safe. Even the journey back to the surface holds a hidden danger that accumulates across a lifetime. 6,000 feet below the surface. No light, no landmarks. A body that has just spent over an hour burning through its oxygen reserves while chasing, catching, and swallowing prey in complete darkness. Now find the surface. For a human diver, even a well-equipped one in much shallower water, losing orientation in low visibility is a genuine emergency. The feeling of not knowing which way is up has caused fatalities in cave diving and wreck diving even at depths of only a few hundred feet. The natural instinct to follow rising bubbles only works if you have bubbles to follow. The sperm whale has no bubbles, its lungs are flat. Its orientation system relies on multiple senses working together. The inner ear contains structures that detect gravity and acceleration, the same basic system humans use to know which way is up. These structures work regardless of light conditions. The whale also has a strong pull from its own buoyancy. As the hunt ends and the whale begins its ascent, the gradual increase in buoyancy that comes from the oil in the spermaceti organ warming slightly provides a consistent upward force, a physical signal pointing toward the surface. Additionally, pressure itself provides directional information. The difference in pressure between the whale's head and tail when it is oriented vertically is detectable by the animal's body. Rising means decreasing pressure on the blowhole end. The whale's body tracks this change continuously. Water temperature also provides a gradient. Cold water sits deep, slightly warmer water sits above it in most ocean conditions. As the whale ascends, temperature gradually increases, providing another consistent signal that points the way up. The whale integrates all of these signals, gravity, buoyancy, pressure gradient and temperature, and navigates toward the surface accurately enough to breach within seconds of an hour-long dive in total darkness. And then, during the ascent, a challenge we have already discussed returns. Speed management. The careful deceleration in the upper water column where pressure changes fastest. The instinctive throttling back that protects against the bends. All of this in an animal working from stored oxygen, with a brain that has been managing a complex hunt for the last hour, returning to air while processing what just happened below. Young whales are less precise at this than older ones. The system improves with experience and age, and the bones of the oldest whales carry the record of that lifetime of pressure. Cut open a tree and count the rings. Each one is a year. The rings carry not just the count, but the story of how each year went. Thick rings for wet years, thin ones for drought. A sperm whale's skeleton tells a similar story. Researchers examining sperm whale bones, particularly from older individuals, have found a pattern of damage that accumulates over years of deep diving. The damage is called avascular necrosis. It occurs when small gas bubbles form in or near bone tissue and cut off blood supply to sections of the bone. Without blood supply, the bone tissue dies. The dead section is replaced over time by a lesion, a spot of altered, weaker material. In human divers who experience repeated decompression events over a career, this damage shows up in the large joints of the shoulders, hips and knees. It is a known occupational hazard of commercial diving. It causes chronic pain and eventually loss of function in the affected joints. In sperm whales, the damage appears in the vertebrae and large joints of the spine in older animals. Younger whales examined by the same researchers show clean, healthy bone. The damage accumulates over time, building up across years of dives. This tells a specific story. The whale's dive system is effective enough that individual dives rarely cause acute injury. But across decades, the small residual nitrogen that does make it into the bloodstream on some dives leaves a trace, one lesion at a time, deposited over a lifetime. An older sperm whale is not the same animal inside as a young one. The deep has carved itself into the skeleton, and yet the older whales keep diving. Researchers tracking individual sperm whales over years have found that animals showing bone damage consistent with chronic decompression effects are still making full-depth dives, still hunting successfully, still travelling the same distances as younger animals in the same group. The damage accumulates. The whale compensates. The hunting continues. What stops a sperm whale from diving is not bone damage from pressure. Researchers have not identified a point at which the accumulated skeletal wear forces the animal to shallow water. What stops a sperm whale from diving is the end of its life. A well-documented 70-year-old sperm whale carries 70 years of dive history in its bones. Thousands of dives. Thousands of battles in the dark. Thousands of returns to the surface. And still, until near the end, the animal descends again. Because the deep is not a place the sperm whale visits. The deep is where it lives. Every dive costs something. 90 minutes of breath held, 6,000 feet of pressure absorbing into every tissue. The slow accumulation of nitrogen traces that write themselves into bone over decades, the risk of a failed ascent, a sudden sound, a faster than safe return to the surface. The sperm whale pays all of this every single day of its 70-year life. Why? The answer comes down to a simple calculation that evolution made long before the first sperm whale ancestor was recognizable as one. The deep ocean is the largest living space on Earth. Over 90% of the ocean's volume sits below 600 feet. That vast dark space is not empty. It holds enormous concentrations of prey that nothing else can reach. The giant squid, the large fish, the other squid species that live at depth, all exist in a zone that almost no predator can enter. The sperm whale is one of the only air-breathing animals on Earth that can access this space. Its diving ability gives it exclusive access to a food supply that no other large predator competes for at those depths. At the surface and in the shallow water above 600 feet, sperm whales would compete with every other large predator in the ocean. Orcas, sharks, dolphins, and tuna all hunt in those zones. Food there is contested constantly. At 6,000 feet, the sperm whale hunts alone. The deep ocean removed competition. The whale paid for exclusive access by becoming the only animal capable of going there. Every adaptation we have covered in this video is the price of that access. The flexible rib cage, the compressed lungs, the massive blood volume, the black myoglobin-saturated muscle, the retia mirabilia protecting the brain, the controlled ascent, the bone wear accumulating across a lifetime. Every single one of those things exists because the food is down there and nothing else can get to it. The sperm whale did not become extraordinary and then go deep. It went deep and became extraordinary as a result. Evolution is a slow conversation between an animal and its environment. The deep ocean asked questions across millions of years. Hard pressure. Total darkness. Prey that fights back. Every generation of whales that could go a little deeper, stay a little longer, hunt a little more effectively in the dark, had a slight survival advantage over the ones that could not. Multiplied across millions of generations, that slight advantage built an animal that reaches 236 decibels, collapses its own lungs on purpose, stores oxygen in black muscle, and grows the largest brain in the history of life on Earth. And it does all of this to get to a place you and I will never see. 6,000 feet below the surface, in water so cold and dark and heavy, it would kill us in seconds. The largest toothed predator on Earth is right now clicking through the dark, listening for something enormous to fight. The deep made it what it is. And what it is extraordinary.